In this segment, we're going to talk more about GPT-3 and some of the latest developments surrounding very large language models. So one of the questions that arose from the kind of work surrounding GPT-2 is, what are the scaling limits of these? And so before GPT-3 came out, NVIDIA trained an 8.3 billion parameter model, which was about 5 times the size of GPT-2, and showed that you could actually get lower perplexity on held out data from this model. So this model itself wasn't actually used that much, but it did kind of suggest that we haven't yet hit the limits of how much these things can scale. And so there was an interesting study from OpenAI about this scaling behavior. And so we have this graph on the left here, where the y-axis is the test loss. Think about it as perplexity on held out language model data and just text. And the x-axis here is compute. So each line here is a separate large transformer language model. And as you go from kind of left to right, you get bigger and bigger models. So they take longer and longer to train. That's kind of represented by the higher amounts of compute, but they also get better and better perplexities. And so the interesting thing is that these all kind of bottom out along this like compute versus test loss frontier, which sort of suggests that, like, given the right configuration of your model, if you if you have more compute to throw at it, you can get better and better test loss. And so they kind of pushed this pretty significantly and found that bigger data and larger numbers of parameters did lead to these kind of smoothly decreasing test losses, as you see in these two new graphs that appeared here. And the critical thing about this is that they actually suggest how you can take big data sets and kind of have a recipe for knowing how much data you need, how big a model you need, and other things like setting hyperparameters in order to get good performance on them. So this is kind of what led to GPT-3, this observation about scaling. And so you can see here in this table that so GPT-3 XL here, this is a model that's basically the size of GPT-2. And then as the models get bigger, all these kind of parameters, all of these hyperparameters that control the size of the model kind of got bigger. They would increase the number of parameters, the size of the number of layers, the size of each layer, et cetera, in order to make bigger and bigger models. So the final thing is what we call GPT-3, which is this 175 billion parameter model that's absolutely massive. So this has to be trained on a kind of high bandwidth cluster because you actually can't even store all the model parameters on a single machine, just based on the kind of memory limitations of GPU hardware. So the kind of main thing that came out of GPT-3 was not just the scaling, though. It was kind of a new way of thinking about learning. So the way we've been talking about learning so far has been through this fine-tuning paradigm. Basically, you see a bunch of examples of data instances here, like these translations from English to French. And we do gradient updates on the model in order to kind of teach it how to translate from English into French. All right, so GPT-3 had a new way of framing this, which was that we wouldn't actually do any gradient updates on the model. Instead, we would put a bunch of examples, or rather just a few examples, because that's all we can handle, into the context of the language model. So what we're seeing here is a language model context, which is translate English to French, sea otter, loutre de mer, peppermint, menthe poivrée, etc., cheese, arrow, blank. So based on your experience in assignment 4, and kind of looking at how much the model is actually able to use kind of far back information in a language model, you might be a little bit skeptical that this can work. And that skepticism would be sort of correct. However, it's really when you get to these huge models that this stuff actually starts to work. The idea that kind of the model can learn from these examples in the context of the language model without gradient updates starts to really take off once you get into these 100 billion parameter plus language models. And the other thing that's kind of critical here is that by having the right natural language prompt, you can actually do a little bit better. So the way that you structure those examples in the context is also important. All right. So the results from GPT-3 were largely emphasizing these few-shot in-context learning settings without gradient updates. And the results are honestly a little bit mixed. Some of the results are pretty impressive. For example, this accuracy on the record data set from a few-shot model is about as good as a large model that's fine-tuned. But some of these other numbers are not that impressive or not that good. But this is still pretty amazing that it's done without any gradient updates and in this kind of few-shot setting where you're only seeing 8 or maybe 16 examples of each data set. So the prompt here is also something that's important, and there's been a lot of work since the GPT-3 paper came out on the topic of prompt engineering. So this is some work due to Timo Schick and Henrik Schütze, which looks at basically having different prompts associated with Yelp reviews. So for example, you can have the text of the review here and then say, all in all, it was blank. And you then put a word is kind of indicative of your different sentiment labels, and you can use this to assess whether the model thinks that this review should be summarized as bad, okay, good, great, etc., which give you these kind of 1 to 5 star ratings. So they have this actually fairly involved procedure, which uses a combination of these different prompts and uses this to kind of bootstrap from small amounts of few-shot data and move up to larger amounts of unlabeled data. So a kind of pretty interesting way of doing few-shot learning here.